Good afternoon. It is 12 o'clock. Welcome back. I'm recording this so that I can upload it and post it to the D2L so you can look back on it again. So I'm not going to waste any time because I know your time is valuable. So we'll just get started here. Okay, so again, here is our post for the day. I'm gonna skip over that first part and start looking at the stuff from our new unit. Right, so it is Unit 4, and the first three tabs in here are open to you, right? The introduction, particle theory of light, and wave theory of light. The way I teach this course, it might be, well, it is definitely different than the way I teach any of the other units in the 4U physics. I teach this one from a bit of a historical perspective. So looking at how we came to think of light the way we think of light. And I know in grade 10, you covered some light stuff, right? We talked about reflection and refraction and all of the properties of light. But the grade 12 version of light, what we're going to look at is not just what light is, what light does, but we're more talking about what light is. Okay, so we're going to look at the different theories that have evolved with our understanding of light. Now, why do I teach it this way? The simple reason is a grade 12 physics student, well, if I were to tell you right now what our current understanding of light is, your mind would explode. Your mind would be like, what? How did we get to that? Well, so I'm taking that question out of your hands and I'm teaching it from that question's perspective. Okay. So I'm not going to read this, but I definitely encourage you to, talks about theories and scientific theories and how we come up with a good scientific theory and how we debunk scientific theories that are no longer suiting our purpose. Okay, so this second sheet says, how do you cast or characteristics of a useful theory? So I'll let you read that. So these scientific theories are models. They take all the information that's available and make a simplified version to explain everything. Okay. It interprets and explains unknown things in terms of known things. So the first two theories we're going to talk about are a particle theory and a wave theory. Okay. I'm going to talk about pool balls or billiard balls on a pool table. Those are particles. We've all seen those before. Well, guess what? We've never seen a particle of light. But if light is a particle, then light must behave like billiard balls. Wait, we've seen water waves before. And if light is a wave, it will behave like water waves do. So taking the unknown and explain it in terms of the known. A good scientific theory takes the separate facts and puts them into a more easily grasped structure for us. So it helps organize and explain stuff, makes predictions about the phenomena that have yet to be observed. So the one that's going to come up is the speed of light. Well, we had no way of actually figuring out what the speed of light was back in the day, but the different models would make predictions about that speed of light, even though we didn't have a way to measure it. Scientific theory or model uses the smallest number of assumptions possible, right? If I have a theory that's got 100 assumptions, well, it's not a very good theory compared to a theory that maybe only has 1 or 2 assumptions. And the last one, very, very important, a good theory is going to be flexible enough to accommodate any new information coming in, right? If your model is so rigid that one piece of new information, if it didn't fit in your rigid box, then your whole theory is debunked, okay? So your theory needs to be malleable enough to accept new information, okay? So we cast doubt upon a theory. Well, obviously, if an observation is made that doesn't fit with your theory, that debunks it. And also, if two different conclusions can be drawn from your theory, that will debunk it for sure. This is just a poem that I found, and it fits very nicely into this this section of the course. So I will let you read it. How does it fit into this idea of theories? I put my my little spin on it at the bottom there, so I'll let you read that at your own leisure. Okay, particle theory. Both the particle theory and the wave theory are set up the same way. There is the whiteboard note that I've provided for you. There is a video talking about that theory, and then there's a question sheet. Okay, the note, the whiteboard note, goes right along with what the video looked at. Now, every time I show these videos, I always have, that's the wrong one, pardon me. I always have people kind of laughing at them because of the poor quality of the video. Like, if you have a look, that's small, there it is, bigger. But it is from the 80s. It is a TVO educational series called Senior Physics. And it walks through this whole historical perspective of why do we think about light the way we think about light. Okay, I like this theory, or sorry, I like this video series. If you don't, guess what? They're only about they say 9 minutes a piece. Okay, so we'll go walk through the whiteboard note right now. Keep in mind that what I'm telling you is not what we think about light right now. It's what we thought about light way back when. Okay, so we start with the ancient Greeks. So way back in the day, you know, back, I call it the good old days when people were wearing bed sheets and eating grapes and just thinking about stuff. Okay, so a guy named Plato, he believed that light started from the eyeball and came out of the eyes and went out. Pythagoras and all of his followers, called Pythagoreans, they believed that light traveled as a stream of fast-moving particles, not maybe originating from the eyes, but only a fast-moving set of particles. About the same time, though, back in ancient Greece, Empedocles, never met the guy, but I hear he was quite a fine guy. He thought that light was more like a wave. So even going back to way back with the ancient Greeks, there were competing theories. Okay, jump ahead a whole bunch into the 1700s, and this is back when we first started looking up at the stars and making observations with stuff up there, and it was determined that the speed of light, a value for the speed of light, and the value they come up with was very, very close to what we know it to be now. Okay. Okay, so let's talk about some things that happen with particles, and we'll compare that to what happens with light, and we can make some observations, or not some observations, we can make some predictions. So imagine these are billiard balls on a pool table, right? I've got somebody here firing billiard balls. I got somebody here firing billiard balls. And these billiard balls, they're traveling in paths that are going to intersect. And eventually, some of these billiard balls are going to hit some of these billiard balls. And what's going to happen? Well, they're going to change the direction that the balls are going. Collisions are bound to happen. That's what happens with particles. Well, guess what? Light doesn't behave that way. And that's a problem, right? If we're trying to make this theory about light being a particle, then we need to have some explanation for why it will behave like a particle or why it doesn't behave like a particle. If you shine two beams of light, those beams of light will pass right through each other, right? Light will carry on unaffected by the other beam of light. So particle theorists came up with the explanations. Oh, okay, well, the explanation must be that these light particles are so very tiny that they will never collide with each other. And it makes sense. If these are great big bowling balls and they're being fired, yeah, the chance of them hitting each other is pretty big. If we reduce that size of those particles down to marbles, well, there's less of a chance of that collision happening. So these light particles must be even smaller than marbles, like teeny tiny particles, and they're never going to collide. Well, that's how the particle theory people explained that there was no visible interference, because these tiny particles don't ever hit each other. Rectilinear propagation, that's a fancy sciencey way of saying traveling in a straight line. Okay, and particles, and you'll see this from the video. In the video, they have a guy on a motorcycle, and when he's going very fast, it appears that his motion is more straight than if he was going slow. This is a guy on a motorcycle going off a cliff. Okay, and if he's going slow, his motion appears to be this trajectory. And if he's going very fast, it's more of a straight trajectory. So just with that little observation, you say, oh, okay, faster moving objects travel in straight lines. And since we know that light travels in a straight line and seems to always travel in a straight line, the speed of light must be really, really, really big. Now, how do we know that light travels in a straight line? Because we have shadows, right? You can block light with your hand and there's a shadow line. If light traveled in if light didn't travel in a straight line, it would bend around that hand and you wouldn't have a shadow. Okay. So now we've got light being made of very fast, small moving particles. Okay, so again, go back to your pool table and take one of your pool balls or billiard balls and push it towards the side of the pool table, and it'll bounce off in a very specific way. And this is a law of reflection where the angle of incidence equals the angle of reflection. The angle in equals the angle out, and that was grade 10 stuff for sure. We knew that. Okay, and that's always the case. And lo and behold, a beam of light does the same thing. Beam of light coming in towards a mirror, hits that mirror and bounces off with the angle of incidence being equal to the angle of reflection. Now, I just want to remind you about this dotted line. Remember, that dotted line is what's called the normal. Okay, and the normal is drawn at 90 degrees to the surface of contact. Okay, and the reason it's dotted is because it's an imaginary thing. So we don't draw it as a solid line, it's a dotted line. And our angles are measured. So this is the angle or the incident ray. And the angle from the incident ray to the normal is our angle of incidence. And on the other side would be our reflected ray and our angle of reflection. But this is good support for the particle theory. Hey, here's particles. This is what particles do. And oh yeah, hey, here, this is what light does. Light does the same thing as particles. Therefore, light must be a particle. Okay. With these particles up here at the pool table, right, when it hits and bounces off, if there is no decrease in speed, collision is an elastic collision, right? There's no change in the kinetic energy. Well, that's what we're saying with light. The speed of light is not going to change just because it hits something. Well, if the speed of light doesn't slow down, it's an elastic collision. So these small, fast-moving, tiny light particles are elastic in nature. Okay, I like this explanation. So this is refraction. Remember, refraction is about going into a new medium. And in grade 10, you probably talked about light going from air into water and from air into diamond and glass and all that stuff. So that's what we're talking about here. We're talking about going into a new medium. Okay? So if we're talking about these particles, okay? And we start off with an assumption. It says, assume that light particles are attracted to particles that make up the medium. Okay, that makes sense, because a light particle has, if it's behaving like a particle and all other particles have mass, then these light particles have mass. Here is a light particle. It is attracted to, so the top medium is air, the bottom medium is water. It is gravitationally attracted to every air molecule up here. It's attracted to this air molecule and this air molecule and this air molecule and this air molecule. It has forces acting in all directions. And if you were to add up all of those forces, you would get a net force of 0. Hold on. A net force of 0. That means that the acceleration would be 0. And that means that this particle traveling in this medium up here would not be accelerating. It would stay at a constant velocity. So that means it's going to travel in a straight line. If I jump ahead and say, okay, well, when this particle is in the water, this same type of scenario would happen. The forces would be different sizes because the water molecules are bigger. So the size of the gravitational attraction would be more. But again, down here in the water, it would be a net force of 0. Where the interesting thing happens is near the boundary layer. So as these light particles are getting closer to the boundary, right, they are being more gravitationally attracted to the water because these water molecules are bigger and have more mass. It's got a larger force pulling it down, which means it's going to have an acceleration down towards the water. Okay, so that means there's going to be acceleration down. So that, what does that mean for this light particle? This light particle is going to speed up, number one, and it's going to change direction. So we are predicting that these light particles are going to travel in a straight line in the air, and when they get to this boundary between air and water, they're going to speed up and they're going to change directions. They're going to bend down towards this normal. So there's would be a normal line here, right? What happens with light? Well, heck, look at light. Here is light traveling in air and it travels in a straight line. When it gets to that boundary between air and water, it does change directions. It bends down towards the normal, just like our prediction up here with particles, bends down towards the normal. So what does that mean for us in this particle theory? That means that, hey, light is doing this thing, and well, if I look at my prediction with particles, these particles are going to speed up as they bend towards the normal. So light must speed up as it's going from air into water. We've just made a prediction. We predicted that light travels faster in water than in air. Now, I don't have any way to show that, but my theory is allowing for us to make that prediction. Now, I know some of you right now are going, well, but that's not what happens. Light moves slower in water. And you're right, light does move slower in water. And because you were paying attention in grade 10 science, you know that to be true. But guess what? The people coming up with this particle theory never made it through my grade 10 science class, right? You're smarter right now than what the people who came up with the particle theory were, okay? Dispersion. Dispersion is white light breaking up into the spectral colors of the rainbow. Okay. In order to explain the colors of the rainbow and this dispersion, we're going to make this assumption that different colors of light are made up of different mass particle sizes. Okay. So this is a triangular prism. We send white light through a prism and it splits up. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Okay. And if we're explaining this rainbow with different particle sizes, think about what this means. Bigger particles have bigger mass and would have greater inertia. And remember, we call inertia is the resistance to a change in motion. So the bigger particles are the particles that are going to stay on the more of a straight line path. The lighter particles have less mass, which means they have less inertia, and it'll be easier to cause them to change their motion. Okay, so you're going to have one mass set of particles here, and as you go down, you're going to have smaller and smaller mass particles. So, comparing the two, well, it makes sense that red particles of light should have the biggest mass. Violet particles of light should have the smallest mass. Diffraction. Diffraction is about spreading out as you go through an opening or around an obstacle. Imagine back in the days when we could go to the store and be around people. I once went to Future Shop on a Boxing Day, lining up to get a big TV, and this is imagine this is the doorway to get into the store, and this is all the people lining up to get into the store. And when they opened the doors, yeah, we all ran towards the door, and we were bumping into each other and bumping into the sides of the door. And as soon as we got in, boom, we got to spread out. That spreading out is what diffraction is. And light does a bit of that, right? As the light particles go through that opening, there is a bit of spreading out. Okay? Not nearly as much as maybe we thought there might have been, but there is a little spreading out. This diffraction also works when you're going around an object, and we'll look at that more with the wave theory. And that's our note on the particle theory. Again, you should be, I hope you are thinking, oh, I'm not sure if I believe that, and that's fine. I'm telling you the historical approach, how we came up with this idea. Again, please watch the program. It maybe does a nicer job of visually showing you some of those things. Okay, so the wave theory note, so this is the whiteboard note that I would use, goes through some of the exact same, well, it's set out the exact same way. I'm going to show you what water waves do, and if water waves do it, and we can show that light does the same thing, boom, makes sense that light must be a wave, okay? So I'm going to start by explaining my diagram here, okay? Here is a reflecting surface. These waves here, so imagine these are crests of a wave. So this is a crest, and this is a crest, and this is a crest. And these crests are incoming wave fronts. So this is incoming wave fronts, incident wave fronts. And those incident wave fronts travel along here until they hit this barrier and they reflect. What I'm pointing at now, this is my series of reflected wave fronts. Okay, Now you see that hitting this barrier didn't change the wavelength. The distance between wave fronts is staying constant before and after the reflection. And you can see that each reflected wave front comes from one incident wave front. So this little piece of a reflected wave front came from part of this incident wave front. And this piece of a reflected wave front came from this incident wave front. Okay, so they don't just appear out of nowhere. Each incident wave front turns into a reflected wave front. Now I can draw, this is called a wave ray, and this is a something that is put in so that we can measure our angles. An incident wave ray is drawn at 90 degrees to the incident wave fronts. And you can see, hey, the angle of incidence equals the angle of reflection. And if I look at light, and this is the same diagram that we used in the particle theory, hey, an incident ray of light hitting something will bounce off with the idea that angle of incidence equals angle of reflection. Hey, water waves do it, and light does it. It just makes sense that light must be a wave. And it doesn't just happen with straight barriers, it also happens with curved barriers. And in grade 10, you did reflection with curved mirrors, right? And there were 3 reflecting rules for curved mirrors. And I'm gonna try and say them and not butcher them. An incident ray of light traveling parallel to the principal axis will reflect through the focal point. So that's what this is doing, right? Going towards the curved surface, parallel to the principal axis, reflecting through the focal point. There was another one that says an incident ray of light going through the focal point will, through the center of curvature will bounce back along itself. And another one, if it goes through the focal point, it will reflect parallel to the principal axis. All of those things are grade 10 stuff. I'm not going to drill home on it. I just want you to remember, hey, light will bounce off a curved surface in a very specific way. And it turns out that water waves do the exact same thing. And these water waves towards this curved surface, and they reflect off as if they're coming from this point, which is called the focal point. So straight parallel incident wave fronts will produce curved reflected wave fronts. Imagine you've got your finger and you're dabbing it in the water of a puddle, right? That's what's being produced. You're producing curved waves coming out. And here is light from grade 10 traveling in towards this curved surface, hitting this curved reflective surface and bouncing through the focal point. Hey, water reflects in a certain way and light does the same thing. It makes sense that light must be a wave. Okay, refraction. Refraction is going from one medium to another medium. So we're going to talk, how do we change, if we're talking about water waves, how do we change the medium? The medium is water. Well, we have to change a characteristic of it. We're going to change the depth of the water. Okay, we're going to have deep water up top here, shallow water down below. Okay, and again, we've got wave fronts coming in towards this boundary layer, and these are going to be refracted wave fronts traveling away. We've got a constant wavelength happening in the deep water, and afterwards is going to be a constant wavelength happening in the shallow water. It's a different wavelength though, okay? Again, I want to make note. I want you to pay attention. Each incident wave front produces one refracted wave front. So this little piece belonged to this incident wave front. This longer piece, well, it belonged to this one, and so on and so forth. And this is through observation. This is what we see if we were to set this up on a water table, right? These water waves with this wavelength, when they go into shallower water, the wave fronts bend and the wavelength gets smaller. And I can draw my wave rays in, and you can see, well, my wave ray bends towards the normal in the new substance. This is what waves do. So if I can find the scenario for light that it does the same thing, it's a very good comparison. And lo and behold, yeah, air on the top, water down below, you have the light ray bending towards the normal. Well, here, bends towards the normal, here, bends towards the normal. The neat thing is in the analysis here right now. So I'm going to come back up here to my water waves and say, okay, the source that made our waves in the deep water is the same source responsible for the waves in the shallow water, right? Because these waves in the deep water turned into waves in the shallow water. So they're from the same source. So they have the same frequency. Okay. Now remember, we used this symbol prime to show afterwards before. Remember when we did that? So the wavelength in the deep water is lambda. The wavelength in the shallow water is lambda prime. So I can see just by the diagram, my wavelength prime, my wavelength in the deep water is less than the wavelength, sorry, my wavelength in the shallow water, pardon me, shallow water wavelength is less than the deep water wavelength. But if they both have the same frequency and they're waves, deep water and shallow water, both still waves, they have to abide by the universal wave equation. So have a look what happens. Frequency stays constant. So that means the speed and the wavelength, they're going to be directly proportional, right? And if the wavelength is smaller in the shallow water, that means the speed is smaller in the shallow water. These deep water waves are traveling faster. These shallow water waves are traveling slower. And if light really is a wave, then the speed of the light waves here in the air must be faster than the speed of the light waves here in the water. We have just made the prediction that light travels slower in water than in air. Now compare that back to the particle theory. Particle theory said, hey, light particles move faster in water. Light particles move slower in air. This is where our two theories go in different directions. Can they both be right? No, they cannot both be right. One is going to be wrong and one is going to be right. Okay. Okay, dispersion. Dispersion, that was our colors of the rainbow thing, okay? Dispersion is really just looking at that refraction stuff again. So this is water waves, very similar diagram to what we just looked at with refraction. Here are water waves coming into this, going from deep water to shallow water, and they bend. I'm going to make this smaller so we can see both diagrams here at the same time. This is still water waves. What's happened from one diagram to the next? I've changed my frequency of my source. So I've changed my wavelength. I've kept the same angles, same angle of incidence. But what you can see is that this angle of refraction is bigger than this angle of refraction. My angle of incidence is the same, but my angle of refraction is different. Okay, so well, what did I change? I changed the wavelength of the incoming waves. Wavelength has some bearing on how much that light's going to bend. Well, what does that mean? Wavelengths of light bend different amounts. The red wavelength of light is different than the violet wavelength of light. And that's why they bend different amounts. Okay? Again, my first two diagrams here, this is through observation. We see this happening with real water waves. And when light shows that same type of splitting up or bending different amounts, it makes sense to have the observation that different colors of light have different wavelengths. And going right along with that, that means different frequencies. Okay. Now, the wavelengths of light are not, this is not something I have measured or the wave theory people measured yet. The frequencies of light, again, they don't have an answer for what those are, but we're making a prediction that relative to each other, these have different wavelengths, and that's why they bend differently. Okay, diffraction. Remember, diffraction is about spreading out while they go through an opening or going around an object, okay? So there's more to the diffraction here with water waves than there was with the particles. So here is a big opening or a big obstacle, okay? And I'll talk about them both together. So I've got a small wavelength and a big opening, or a small wavelength and a big obstacle. And you can see there's not a whole lot of change. The waves just carry on through. There's a little bit of spreading out at the edges, and more so as you get further and further away. But immediately after the opening, there's no spreading out. I call this a dead spot. This is a spot where there's no waves happening above and below. For an obstacle, well, immediately after that obstacle, there's a dead spot. There's no waves here. And that's not always the case. If I set up a smaller opening or use a smaller obstacle, then yeah, there is more significant diffraction. These water waves, when they go through this small opening, they spread out like this. The pattern of waves on this side of our opening is a circular wave front. It's like here at the opening, it's like you've got your finger dabbing in the water, producing circular waves coming out from that, okay? Here, a small obstacle, and you can see there's a little dead spot right afterwards, but pretty soon those waves take over that dead spot and carry on, okay? So what is this showing? The size of the opening or the size of the obstacle needs to be closer to what the wavelength is, right? If the opening is bigger than the wavelength, you don't get any significant diffraction. These are diagrams straight from your textbook. It's showing you the exact same thing. And what do we get? This ratio, the wavelength over top of the slit width or the width of the obstacle, in order to get significant diffraction, that ratio needs to be greater than or equal to 1. What does that mean? That simply means wavelength and slit width need to be close to the same size. Okay. Well, guess what? We don't get a whole lot of diffraction. We don't get a whole lot of diffraction with light, right? We don't, you know, I've got my hand here. Light gets stopped by my hand. That's why I get a shadow. Well, what does that mean? That means that, hey, the wavelength of light isn't the same as the width of my hand, right? We get significant diffraction when the slit width is really small. Tiny, tiny, tiny openings and micrometers, right? For a tiny obstacle like your hair, a piece of human hair, that would be an obstacle that you would get diffraction around. But in everyday life, we don't see significant diffraction with light. why with the door open to the hallway, I could hear, if we were in school, I could hear kids out in the hall talking, but I couldn't see them because the light from the hallway couldn't come in through that doorway and spread through the room. Okay, but sound waves could. The wavelength of a sound wave would be closer to the width of that opening for the doorway than the light waves are. Now, tomorrow we are going to look at diffraction of light, I think, okay? And I'm going to show you a pattern that looks like this. Don't worry too much about that right now, though. And that is me walking through those whiteboard notes, talking about wave theory of light and particle theory of light. Okay, couple of things that I didn't touch on and I want to make sure I do. Particle theory was pushed and backed by Sir Isaac Newton. Okay, so he was the big guy for the particle theory. And everybody's heard about Newton. Newton had like rock star status back in the day. If they could have t-shirts made, everybody would be buying a Sir Isaac Newton t-shirt, right? He was awesome. And it wasn't just scholars that knew him, right? Academics knew him. The general public knew him. He was in politics. He was, I think he was knighted by the Queen. Everybody knew him. Okay. Wave theory, they had a guy named Huygens. And I other than teaching wave theory of light, nobody has heard about Huygens. Nobody was buying a Huygens t-shirt. Okay, so Newton's prominence in society propped up that particle theory more than it probably should have been. Okay. But it was the theory itself that ended up being the downfall. And again, we'll talk about light interference and light diffraction and speed of light. All of those things are going to end up being the demise of the particle theory.